You open a website, the page somehow appears for you. You join a video call and you receive the audio and video from the other side. Therefore, from outside the internet feels clean, but underneath it's chaos. Packets get delayed, packets arrived out of order, sometimes packets disappear completely. And somehow, most of the time, you never even notice it. That's the magic of the communication protocols like TCP. TCP made the unreliable internet field reliable. But here you may ask this: if TCP is so good, why do we still need UDP? Or why do we still need other protocols? Why was TCP not enough? To answer that, we need to understand what TCP actually promises. TCP gives an application a reliable ordered stream of bytes. That means if one side sends the byte for a web page or an API response, for example, TCP tries to make sure the other side receives the same bytes in the same order. This sounds really simple, but the network underneath does not provide that guarantee. IP, the layer below TCP, is the best effort. It tries to deliver packages, but it doesn't promise they will arrive or they will arrive in order. So TCP adds reliability on top of an unreliable network. This is how TCP works. First, it establishes a connection. Before data flows, the two ends perform the famous three-way handshake: synchronization acknowledgement, and another acknowledgement. But do not think of this as just protocol vocabulary. Think of it as both sides asking, "Are you there?" Then there's a response, "Yes, I'm here." Then another response from another end, "I heard you." More importantly, both sides agree on sequence number. And sequence numbers are where TCP becomes interesting. TCP numbers the byte stream, not just packets, bytes actually. So the receiver can say, "I have received everything up to this point. Here is the next byte I expect." That response is called an acknowledgement, or ACK. ACKs are the feedback loop of the TCP. They tell the sender what has arrived and what is still missing. If data disappears, TCP can detect the gap. If there is a packet loss, the receiver keeps asking for the next missing byte. The sender eventually retransmits the missing data. That is why a file can arrive correctly even when some packets fail along the way. But if TCP waited for every packet before sending the next one, it would be painfully slow. Imagine sending one packet from Europe to North America, waiting for confirmation and only then sending the next packet when you get that confirmation. The connection would waste most of its time waiting. So TCP uses a sliding window. The sender is allowed to have multiple chunks of data before receiving an acknowledgement. As ACKs come back, the window moves forward. More data can be sent, of course. This is how TCP balances reliability with speed. It keeps the network busy without losing the track of what has arrived. TCP also has congestion control. So it watches for signs of congestion. It starts carefully, which is called a slow start. It increases transmission rate, which you can show it as a sawtooth graph. But when it sees packet loss or other congestion signals, it backs off. TCP is basically negotiating with the network in this way: how fast can I send without making everything worse? This made TCP one of the most important protocols ever created. It gave applications reliability, ordering, retransmission, flow control, and congestion control without every application developer having to implement those things manually. For web pages, file downloads, emails, APIs, and many traditional applications, this was exactly what we needed. So why is TCP not enough? The reason is simple. TCP's greatest strength also becomes its weakness. TCP guarantees order delivery. The application receives bytes in the same order that they were sent. That sounds perfect until one packet is lost. Imagine packets 1, 2, 3, 4, and 5 are sent. Packet 3 disappears. Packets 4 and 5 may still arrive at the receiver side. The receiver has them, and they're real data and useful data. They're not corrupted, but TCP cannot deliver them to the application yet because the packet 3 is missing. The byte stream has a gap, so packets 4 and 5 must wait. This is called head-of-line block. TCP does not only waiting for missing data, it can force correct data to wait behind missing data. For many applications, that is acceptable. If you are downloading a file, you want the exact bytes in the exact order. Waiting is better than corruption. But for real-time system, waiting can be worse than losing data. Think about a video call. If one video packet arrives late, do you want to call to freeze while waiting for it? Usually no. By the time missing audio arrives, it may no longer matter. The conversation has moved on. The same is also true for online game. If one old position update is lost, you usually do not want the game to pause and retransmit it. You want the newest state, and in these cases, TCP's reliability can become an issue. That is where UDP enters the story. UDP is much simpler than TCP. It sends datagram. No connection setup like TCP, no built-in retransmission, no guaranteed ordering, no reliable byte stream. It's like that you add your envelope to the pigeon and just release the pigeon hope that it will arrive at the destination. And at first, this sounds really bad. Why would anyone want fewer guarantees? It's that because fewer guarantees also means that you have more control over the protocol. UDP lets the application decide what reliability should mean. A video call may tolerate some packet loss, but it cares deeply about latency. A game may ignore all the state updates and only care about the newest one. DNS often wants a small request and a small response without the overhead of full TCP connection. With UDP, the application can build exactly the behavior it needs. Maybe it retransmits the important messages. Maybe it ignores unimportant ones. Maybe it adds its own ordering. Maybe it doesn't. The key idea is this: UDP is minimal because some applications do not want TCP's exact version of reliability. So when people ask which one is better, the answer you may give is this: better for what? If you are downloading a file, TCP's ordered reliability is exactly what you want. If you are building a real-time game or call, UDP may give you the control that you need. This is why TCP is not enough. TCP was one of the reasons that the internet became usable, even in the cellular communication net, especially in 4G and some of the mobile broadband 5G use cases. But nowadays the use cases are changed, and for each different use case, we need different requirements. Until the next video, good morning, good afternoon, and good evening. Bye.